Not everyone has an ideal location for photovoltaics. We will simulate the potential of non-ideal panel orientation and partial shading. Whether an investment is profitable or not does not only depend on the physical constraints. We show an example with consumption profiles, electricity tariffs, and a battery buffer. In this episode, we look at an interesting example where our simulation tool can clarify whether investing in photovoltaics is worthwhile. If you have an ideal location with ideal orientation, then of course you know that an investment is economical. And there are usually many examples for this. However, if your location is not ideal, and the orientation angles of your solar panels are unfavorable and there is even shading, then the decision to invest is not so easy. We will simulate a location that has the said disadvantages. I will explain step by step how we model the different influences and show what effects the physical boundary conditions have. The business case at the end will then show us under which economic conditions, such as electrical tariffs and system prices, an investment can be worthwhile. And of course, now comes the inevitable clue from our monster. Don't forget to like the video and subscribe the channel. Our situation is as follows. Our roof pitch is 34 degrees, which is actually not bad. As a result, the elevation angle for our photovoltaic panels is around 56 degrees, which is close to the optimum. Additionally, we want to attach panels to a dormer window. For these, the elevation angle is 85 degrees, as you can see in the picture. However, the horizontal orientation of the house is quite unfavorable. The halves of the roof face east and west rather than south. For our simulation, I divided our solar generator into 3 parts named A, B and C. Now let's look at the shading. It can be estimated using the sketch and the course of the sun on site. On my latitude, the highest sun position is 64 degrees in summer and the lowest in winter is 18 degrees. Of course, one could also simply observe the location for the critical times throughout the year and then take appropriate notes about the shading. But we don't want to wait that long. For the solar generator A, I estimated from the sketch about 10% shading in June and 30% shading in December. During the remaining months, the transition between the given minimum and maximum takes place. Shading happens every day between 8 am and 2 pm. The same estimations can be done for generators B and C accordingly. I chose a standard size of 1 meter by 1.67 meters for the solar panels. This results in the possible number of panels on the roof for the generators and thus also the peak power that we can install. In total, we get over 7 kilowatts peak. Okay, we have the inputs for simulating our solar generators ready now. I have summarized them here. I have already explained all the functions of the tool in episode EX06. It might be worth to watch the episode again, as it also explains how to use the tool anywhere on Earth. Of course, the site-specific yield is important. In my case, I have already entered these for my location on the resources sheet. In episode EX07, I also explained how to get these for each location on Earth. I think it's the best method. So instead of searching for it for a long time, just watch the episode EX07 again. We go straight to the generators sheet and enter the inputs we just worked out there. Once we have entered our latitude, longitude and time zone, we are good to go. We fill in the peak power as well as the azimuth and elevation angles that we found. We also have a horizon angle, which is 7 degrees here. I have already entered the shading for the months, but left out the times. As a result, the shading does not yet have an effect in the simulation. The tool has now already calculated the yields of the individual generators without shading and gives us the percentage compared to the maximum possible yields. These we would have if our panels could be optimally oriented. Then I enter the times of the shading. For generator A, partial shading appears from 8 AM to 2 PM. Generator B is partially shaded from 2 PM to 8 PM. And for generator C, we have partial shading from 3 PM to 7 PM. We then immediately get a new calculation of the yields, which of course turn out to be a bit worse due to the shading. In the graphs on the right, we can see that we will get relatively good power delivery throughout the whole day, due to our panels being east and west oriented. That actually brings a little more power in the morning and in the evening. At the bottom of the sheet, we see in the summary that we produce relatively little energy during the winter period. That is normal on my latitude. However, in our case, besides the non-optimal orientation, the shading has an additional negative effect during the winter. In total, we produce 5,524 kilowatt hours over the year. Here is the summary of the solar generators. Unfortunately, the big solar generator A has the least efficiency compared to the maximum we could achieve with the optimum orientation. So overall the efficiency is only 66%. We keep that in mind. We go to the sheet consumers. After we have defined and simulated the solar generators, we naturally want to know how our consumption behavior fits in with them. First, let's just look at the consumption for our household. For this, I use the standard load profile for households, which I have adjusted a little to better reflect our usage behavior. The annual consumption corresponds then to what we actually have. We go to the sheet Overview Year. Our annual energy production is significantly higher than our consumption. Unfortunately, We also see that we have a large surplus in the summer and a deficit in the winter. Let's take a closer look at a day in winter and a day in summer. We go to the battery and analysis sheet. We see that on January 1st we will use all the electricity we produce ourselves. But that's not nearly enough to cover the demand. The blue part is our own consumption and the red part is the consumption from the grid. On June 1st the situation is very different. During the day we produce much more electricity than we consume, and at night we still consume electricity from the grid. As a result, our own consumption is relatively low. Most of the energy is fed back into the grid. We don't really want that in Germany, because we get very little money for it. Our grade of autarky is not bad at 42%. This is because we have a high level of overproduction and still cover the evening hours quite well when we still have a lot of consumption. However, I have to say that the 42% is somewhat optimistic, since we do not take into account the volatility of sunlight and consumption peaks in the minute range in our simulation. As soon as we use a battery, however, the simulation becomes relatively accurate because these fluctuations are then buffered very well. Let's have a look at the economics sheet. Here I have entered the current electricity tariffs and the system prices for Germany. Our little business plan doesn't look very good. It takes us almost 20 years to get our money back. With higher electricity prices, as can be expected in the future, the business plan would look a little better. Let's try a battery and see whether it can bring an improvement. For a rough estimate of the battery size, you can always see your average daily consumption here. Let's just take a battery of this size. And we see immediately that the degree of self-sufficiency increases significantly over 70%. It also improves the business plan. We achieved a return on investment a few years earlier. Okay, it's still the case that we are feeding a lot of energy back into the grid for little money. We could use that with an electric vehicle, right? Let's take a look. We go back to the consumers sheet. There is a section called electric vehicles. The logic is always the same. I simply enter here that we use the electric vehicle all year round. It should be charged in the evenings during the week and during the day on weekends. In our example, we would cover about 15,000 kilometers a year and use about 3,500 kilowatt hours. Thus, our consumption would be about 1000 kilowatt hours higher than our generation. We now have to increase our battery a bit, for example from 8 to 16 kilowatt hours. With that measure, we are increasing our own consumption again and reducing grid consumption. Looking at our small business case, we now see a return on investment after about 12 years. So, that is already a significant improvement. If you were to use electricity tariffs here, as you have to pay at charging stations, then the return of invest would come even much faster. We see that although our location is actually not particularly well suited for photovoltaics, there are still scenarios in which the investment would be worthwhile. The insights and the summary. The non-optimal orientation of the solar panels reduces the yield by around 30% compared to the maximum possible yield. The shading reduces in our case the annual yield by a further 4%. Unfortunately, it has a particularly strong effect in winter when we have little yield anyway. Disciplined consumption behavior can improve self-consumption and the profitability of a system. A battery brings some convenience in terms of consumption and can further increase profitability. However, the electricity tariffs for grid consumption, self-consumption and feeding back into the grid also play a crucial role. Try it out. It's really fun to play with the different parameters in order to support your decision making. In this way, you can, for example, play through future tariffs, lower system prices, etc. Or, if you are thinking about purchasing an electric vehicle, air condition, small office, etc., you can simulate whether this could improve the profitability of your system. How do you think about the possibility of simulating all this? Write me in the comments. Now, stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.